Welcome back, everybody. So today we're going to look at the notions of homomorphisms, embeddings, isomorphisms, automorphisms, all like kind of morphisms from one structure to another. So this is the notion most of you guys, well, I hope all of you guys remember from algebra, where you saw some examples, essentially, some particular cases of these guys for particular classes of structures. For instance, here's one example. If you guys remember, a homomorphism of groups from a group G to a group H. So here the E and the I are the identity of the groups. The E is for the G and the I is for the H. So those are the identity elements. And let's say this one has a multiplication operation that is called star, and this one has an operation that is called all times. So a homomorphism from G to H is a map. It's a function from G to H, which maps identity to the identity and which preserves the operation. And you have that whenever you have G1 and G2 in G and you multiply them, and here is G1 star G2, you get the same thing on the other side. So if here is H of G1 and H of G2, then when you multiply them, you get the corresponding guy. Alright, so that means if you multiply before applying H or you multiply after applying H, it doesn't matter, you get the same result, right? So notice this operation here is in the G side, while this operation here is in the H side, because these guys belong to H. Good, okay, so that's a homomorphism of groups, which I hope you guys remember from abstract algebra. And for instance, let's look at a few examples of these guys just to see what these guys were. So let's take the group Z with 0 and plus, and the group of Z2 of 0 plus, where if you guys remember, Z2 is the group that only contains two elements, 0 and 1. And we can define H from here to here by defining H of n equals 1 if n is odd, and 0 if n is even. So this is a homomorphism of groups. So the 0 gets mapped to 0. And if you add two elements, if you add two integers, why is it that preserved on the other side? Well, because if you add two even integers, which means we should give you 0, you're gonna get 0. You're gonna even, which is 0. If you add two odd integers that give you 1, you should get even. So, but 1 plus 1 here is 0, and so on and so forth. 1 even plus 1 odd is going to give you an odd, so 0 plus a 1 is going to give you a 1. So you can check all the combinations and see that it's actually a homomorphism of groups. Just a reminder. The same story was for other structures. For instance, homomorphism of rings. And here in a ring, we have more structure. Now we have a 0 and a 1 and a plus and a times. And in the other ring, we have a 0 that we call O and a unity that we call E, and an O plus and an O times. And these are two rings. They could be anything, like the real or the rationals or the complex numbers or the ring of polynomials. And they satisfy that to be a homomorphism of rings, you need to satisfy that the 0 of one goes to the 0 of the other. The identity for multiplication of one goes to the identity multiplication of the other. And that both operations are preserved. A plus goes to plus, times goes to times, right? So that's a homomorphism of rings. So it preserves all the structure, essentially. If you have order rings, for instance, which I guess is one you haven't seen in algebra, well, you also have an order operation, an order relation, sorry. Ordering is a relation among the elements, like for instance, the integers with the usual ordering or the reals with the usual orderings. Then on top of having a homomorphism of rings, you need to have that the ordering is preserved, right? So that would be a homomorphism of order rings. it preserves also the ordering. When you map two things, if G1 is less than G2, when you map them, you get something less than the other, preserving the order. Okay, so we can now imagine how to generalize this definition to all structures. So here is the definition, which is it's a bit long, but only because we are just trying to do it in full generality. But there isn't that much to it. This is not, it's essentially a generalization of this, but done, no, just taking care of all possibilities. So okay, so let's suppose we have a vocabulary tau. A vocabulary tau has some constant symbols, some function symbols, and some relation symbols, right? So in this case, tau had 2 constant symbols, 2 function symbols, and 1 relation symbol. Let's just consider the general case. And now let's take 2 tau structures, M and N. So M has domain M and N has domain N. And we have interpretations. To be tau structures, we need interpretations for the constants, functions, and relations on the vocabulary. And we are going to call them like this. So the interpretation of the constant symbol C1, we're going to denote it by C1 superscript M in the M structure and superscript N on the N structure. Okay? And the same for F, for the function symbols and the relation symbols. So essentially what we have here is, so F, let's say that one there, F1 is a function symbol, so a character, and F1 superscript M is not a symbol. This one is a function from N to whatever the additive is of that function to M. Okay? So when we put the superscript M, we're not talking about the symbol anymore. Now we're talking about the actual function representing the symbol in this particular structure. All right. So we say that a homomorphism from M to N is going to be a function, again H, from defined everywhere in the domain of M to N, which preserves all the structure. So what do we mean by preserve all the structure? For every constant symbol in M is going to be mapped to the corresponding constant symbol interpretation of the constant symbol in N. For every function symbol, when we look at the interpretation in M, if you apply it to a bunch of elements in M, and then we apply H, that's the same thing as first applying H, and then the function symbol. Alright, so for instance, what I'm saying here is that if you have elements M1 up to Mk in the structure M, when we apply H, we map them to now N, right? So H goes from M to N. So we get a bunch of elements of N. And now we're saying that if you apply F on each of the two sides, here we apply F as interpreting the structure M, and here we apply F interpreting the structure N, which is two different functions. They belong to different structures. But what we get is that the corresponding values that we get are also match through H. Okay, so if you apply H first and then F, or F and then H, we get same result. Okay, so that's what it means to preserve the structure. That this function on M, when you commute it with the homomorphism, you have the interpretation in N. And the same story for the relations. If you interpret a tuple belongs to the interpretation in M of R, if and only if the image of that tuple through H belongs to the interpretation of that relation in N. Okay? So those are essentially these things up here. So this is the case for functions. If you apply plus first and then H, it's the same as first applying H and then the plus. Well, but the plus, each plus is the corresponding to each structure. For relation, if you compare these two elements according to the ordering in G, it's the same as comparing the images of these elements under the ordering in H, right? So that means the whole structure is preserved. So that's a homomorphism. Okay, so there are some special kinds of homomorphisms that are going to be very useful. Homomorphisms by themselves won't be that useful for the class, but embeddings will. So an embedding is a homomorphism that is one-to-one. That's the only property. And actually, if you think about what it means to be one-to-one, one-to-one means that M1 equals M2 if and only if H of M1 equals H of M2, right? That's what it means for H to be one-to-one. So essentially saying one-to-one means that you preserve equality in M, this is in the structure M, and this is in the structure N. You preserve equality, which is, equality could be seen as a relationship. And here we are saying that we need to preserve all relations. We didn't say anything about equality. In embeddings, we also have to preserve equality. And of course, that's something that we want for the homomorphisms that we're going to be considering. And of course, that's something that we want to have nice properties. Okay, so if an embedding is also onto, that means it's a bijection, we say that it's an isomorphism. Okay, so an isomorphism is an embedding that is also onto. And let me remark that the textbook uses isomorphic embedding to just what I'm going to just call embedding, plain embedding. And for me, and actually for everybody in algebra, isomorphism is the word you use when you have a bijection. So you preserve the structure and you preserve it essentially back and forth. Another special kind is automorphisms. So an automorphism is an isomorphism from a structure to itself. Okay? So, and they're going to be very useful. We're going to see that in a minute. So let me mention a few examples of isomorphisms. I mentioned this one in class the other day. So let's suppose we have the group R0 plus, and we're going to map this to R1 times. And the map is going to be H of R equals e to the R. E the exponent e. And then why is this a isomorphism? Well, it's one-to-one, as we know, and it's onto. Well, okay, sorry. We need positive reals to make it onto. So let's make it to the positive reals. Now it's onto, it's one-to-one. And what else do we have? We have that E of 0 is 1. And E of S plus T is equal to E of to the S times E to the T. Right? So plus goes to times. So this is an isomorphism between these two structures, which are like quite different, right? One is plus, one is times. They're both groups. As for example, for automorphisms, because there are many, let's think of one. So here is one. R0 plus, H goes to R0 plus 2. Same structure. You can, so in an automorphism we cannot change the structure, but with the map it's not going to be. But the identity is always an automorphism. Let's look at a more interesting one. If we apply to R, I want to get negative R. Is this an automorphism? Well, yes. So H of 0 is negative 0, which is 0, and H of R plus S is negative R plus S, which is the same as negative R plus negative S, which is H of R plus H of S. Right? So we can pull the plus outside of the H, so that makes it an automorphism. Cool? Okay, so next video we're gonna show some nice properties about these guys.